This class, the recording is started and we are at 9:31. Once again, we talked about how to open a semaphore, close a semaphore, remove a semaphore even. And we saw that they are very similar to files. We have the same flags, or create or exclusive. We have permissions, just like with files, read, write, execute for the user, the group, the others. So that's the way that, in order to answer the question of Mr. Nevzat, the way to control the permissions, plus of course the fact that they have a name and that name might not be available, of course, to everyone. Yeah, so what about the actual operations? How do you post? How do you wait? How do you signal? I mean, those are the things that we haven't seen yet. So, semaphore operations. Now, as we said earlier, there are two main operations, two main things that you can do with a semaphore, regardless of the type of the semaphore. You can wait on it, you can post it or signal it. Same idea. Now, as far as waiting is concerned, however, if we look at the man pages, you will see that there are three system calls that are available, all for waiting. Now, what's the difference between them? Now, you can see that the first two, they accept, well, the pointer to the named semaphore to wait. So basically, when you call them, what they do is they decrement, azaltıyorlar, they decrement the value of the semaphore by 1. Every time that you call it, sem wait, you decrement the value of the semaphore by 1. And if the value of the semaphore is greater than 0, it will decrement it and return immediately. If, however, the value of the semaphore is already 0, the process that called semWait will block until some other process increases the value of the semaphore, in which case it will decrement it and then return. The difference between semWait and semTryWait is that semTryWait is the non-blocking version of semWait. So if the value of the semaphore is greater than 0, semTryWait similarly will decrement it and immediately return. However, if the value of the semaphore is already 0, semTryWait will immediately return instead of blocking, but it will return with the error E again. So you will know that the semaphore has the value of 0, and that's it. That's the only difference. Sem-timed wait also has, well, it blocks, but with a maximum waiting period, but do not use it. It is not portable. So either you use sem-wait or sem-try-wait. In general, try to avoid sem-try-wait as well. Well, if you have a synchronization problem, better solve it by using sem-wait. Any questions about sem-wait and sem-try-wait? Okay, let's continue. How about increasing the value of the semaphore? Well, in that case, we have semPost. We have semPost, which very simply accepts as a single argument the semaphore of which the value we are going to increase. And it returns 0 on success or -1 on error, with errno being set. And it's quite straightforward. I mean, whatever the value of the semaphore is, it will increase it by 1. And that's the whole idea. So if there are some other processes that were blocked waiting for the value of this semaphore to increase beyond 0, they will be woken up. What does it mean to be woken up? So that means they will be taken from the queue of blocked processes and placed to the queue of ready processes. Are they going to execute immediately? Maybe, maybe not. We don't know. What is certain is that once you perform a post, so in other words, a signal, so in other words, increase the value of the semaphore by 1 and only by 1, those processes that were blocked, one of them will be selected to wake up. So if you have, for instance, n processes waiting for the value of this semaphore to be greater than 0 in order to complete their wait operation, after this post, one of them will wake up. Only one of them. And by wake up, I mean that process will be placed from the queue of blocked processes to the queue of ready processes. Which one will wake up? Is the kernel going to wake up the one that has been sleeping the longest? Is it going to wake up the one that just started waiting last? We don't know. We don't know, and there is no guarantee, there is no way of knowing which process will be allowed to continue if you have more than one processes blocked on the semaphore. Do not ever make any assumptions in this direction. Asla varsaymayın, post yaptıktan sonra bloklanmış olan süreçlerden hangisinin uyanacağını. Bu semaforu bekleyen n tane süreciniz varsa ve biri post yaptıysa kimin uyanacağı belirsiz. Herhangi biri uyanabilir. Tamire çekirdeğin elinde ve bilemezsin. Öngöremezsin. Bu konuda önleminizi alın. Varsaymayın. Okay. Now, something that I forgot to tell you maybe. No, I didn't forget to tell you. Okay. SemGetValue, another system call available for us in order to deal with semaphores. Now, SemGetValue, as the name implies, is a function that returns the current value of the semaphore. So it doesn't modify the value of the semaphore. SemGetValue simply, it's a get method, simply tells you what the value of that semaphore is. Where is that value? It is placed in the second argument sval. It returns 0 on success and -1 on error. So if you call it for a certain semaphore, in that case, when it returns, sval will contain the actual value of that semaphore. Now here, just be careful depending on what kind of a system you're using. Now, it can return a positive value, a strictly positive value. So 2, 3, 4, 10, 15, whatever. If the semaphore is blocked by 1, 2, 3, I don't know how many processes, then in that case, it can return 0. And in Linux, it will return 0. However, in some systems other than Linux, it can also return a negative value. For instance, -1, -2. So what does it mean for a semaphore to have the value of -2? It means that there are two processes waiting, blocked, waiting for that semaphore. Now, let me repeat that. This behavior, so having a negative value, does not happen in Linux. It only happens on certain systems, a minority, a small percentage of systems. So do not assume that behavior will be taking place. In Linux systems, regardless of whether there are 2, 3, 1, 10 processes waiting for the same semaphore, if you use SemGetValue, the value that you will get is 0. So it will not return a negative value representing the number of processes blocked on this semaphore. It will just return 0, showing that the semaphore has a value of 0. So be careful on this. So do not be surprised if someday you see a negative value, and you will see a negative value and you will say, Erhan Hoca lied to us. He was saying that semaphores cannot have negative values, but there you go, it has a negative value. No, that happens on only a very small percentage of systems that are somewhat POSIX compliant. According to the POSIX protocol, it is not supposed to, a semaphore is not supposed to have a negative value. And that's how it behaves in Linux. But of course, there are different versions of POSIX too, so it changes all the time, so you never know. Maybe in the next version of POSIX, negative values will be supported. Who knows? So you have to stay updated. You have to keep track of it. Now, let's leave named semaphores aside. And now let's look at unnamed semaphores. So unnamed semaphores means that we have to make space for them. So we have to create a shared storage area for them in order to store them. So they don't have a name. So if they don't have a name, how do you create them? How do you open them? So they have different functions, a different set of functions in order to manipulate them. So now we are looking at unnamed semaphores. Now before, the semaphore had the value of SemT. Now let's see what is happening now. Now unnamed semaphores, also known as memory-based semaphores, are also variables of type SemT, that are stored in the memory allocated by the application. So not in kernel memory, but in user memory. The semaphore is made available to the processes or threads, you can also use it among threads, that use it by placing it in an area of memory that they share. So if we are talking about threads that exist in the same memory space, we will talk about threads in a few weeks. In that case, this is very easy. You just make the semaphore a global variable, and that's it. The global variable is shared and is accessible by all the threads living under the same process. If, however, you want to synchronize multiple processes, well, in that case, you need a shared memory region, a memory region specifically created for shared access among processes in order to store that semaphore. Now, operations on unnamed semaphores, they use the same functions that are used to operate on named semaphores. So you can use the same functions, sem unlink and etc., in order to sem close, etc., in order to manage these semaphores as well. But in addition, you also have two more functions. Those two functions are sem init and sem destroy. Now remember, we do not have a name, so sem open cannot be used. So instead, how do you initialize the semaphore? Now sem init, as the name implies, init will initialize the semaphore. Sem init initializes the semaphore and informs the system of whether the semaphore will be shared between processes or between threads of a single process. So how do you intend to use the semaphore? Between processes or between threads of the same process? It is at sem init that you tell it to the kernel. And of course, you have sem destroy, which we didn't have earlier, in order to destroy a semaphore. Okay, let's look at examples. Sem init. Here we have the pointer to the semaphore. Okay, so for the semaphore that we're going to initialize. The integer that denotes whether it will be shared between processes or threads. So if it is 0, p shared, that means the semaphore is to be shared between the threads of the calling process. If this is the case, well, in that case, it is usually either a global variable or a variable allocated in the heap because it is shared across threads. If, however, p shared is not 0, then the semaphore is to be shared between processes. In that case, it must be the address. So this pointer, the first pointer, must be the address of a location in a region of shared memory. Okay. And of course, the unsigned int value, which will give the initial value of the semaphore. Mr. Nevzat says, is it possible to change semaphores in handlers? You mean signal handlers? Depends. Depends. For a certain type of a semaphore, it is safe. For another type of a semaphore, it's not safe. We will get to that. We have a slide just for that. An example on how to use sem init. Now, this is, well, it's a peek into the future. We haven't talked about threads yet, I know. This is just a small example, a very short example of how one would use semaphores if you had multiple threads that you want to synchronize. We haven't talked about threads. We will talk about threads in a few weeks. This is just to give you an idea of what's happening with threads. We are not interested in it yet. It's just for educational purposes. So here, for instance, we have, first, let's look at the main function. So in the main function, we create two thread objects, T1 and T2. We get the number of loops as a command line argument. Now, sem, where did sem come from? Sem is a global variable. Okay, sem is a global variable. So that means it is shared across threads. So it is in the same memory space of all of the threads living underneath this process. We will talk about that during the week on threads. Here we initialize it to 1, its value. We are giving a p shared value of 0, telling the kernel that this semaphore will be used between threads. We create thread 1. We also create thread 2. And we are telling it to execute each thread. We are telling it to execute thread func. And we are giving it one argument, loops. Then, similarly to the wait system call, here we are waiting for the threads to terminate, just like the wait system call when a parent process waits for its children. And then it simply prints on screen the value of a global variable glob. Now, basically, the idea is that each thread in a separate flow of execution will execute the function thread func. And inside it, what do? Well, they just simply execute a for loop, loops times. And inside it, they first wait on the semaphore, do some operations, and then post the semaphore. And remember what I told you. Whatever statements you have between a wait and a post, those statements are protected. They are protected in the sense that that is the only process or thread capable of executing them. And basically that's it, capable of executing them. So basically it's a critical section. We will talk about critical sections in the future. The main idea is that whatever statements you have between a wait semaphore and a post semaphore, that means that is the only process, so that only one process is able to execute those statements, and all the other processes synchronized on the same semaphores are blocked on the wait and cannot be executing these statements while you are executing them. So even if the kernel interrupts you after the second statement, you can be certain that no other process synchronized on these semaphores can continue executing these statements. So whatever you are doing here, no other process can ruin it. That's the protection of wait and post. So this was a short example on how to use threads and semaphores. We don't care about it right now. We will talk about threads in the upcoming weeks. Now, before looking at the case of processes, let's look at also destroying, how to destroy unnamed semaphores. Now, the semDestroy function, well, just like semunlink, it destroys the semaphore sem. Now, semaphore sem has to be an unnamed semaphore, so do not try to call this with named semaphores. It will do weird things. So semDestroy only works with unnamed semaphores, and it is only safe to destroy it if no processes or threads are waiting on it. After an unnamed semaphore has been destroyed, it can be reinitialized. So just because you have called semDestroy, it doesn't mean that it is going to disappear. Remember, where is the semaphore living? It is living in shared memory. And basically, calling semDestroy is pretty much the same thing as saying to the kernel, I will no longer use this semaphore. We are done with it. The trick is, you must not call semaphore semDestroy if there are other processes or threads waiting on it. So you must be certain that whoever is working with the semaphore, they are done working with it. Then you call semDestroy, and that's it. You have no more connections to that semaphore. That process has been removed from the table of the kernel where it keeps track which process handles which semaphore. Does this mean that the semaphore has disappeared from memory? No, it doesn't. Since this is not a named semaphore, which means that since it is not maintained by the kernel and it lives in shared memory, then it is up to us, the processes that are using it, to free that memory. And only after freeing that memory will the semaphore disappear. So semDestroy, after everybody's done working with it, after all the waits have terminated, semDestroy, and then finally call free in order to deallocate that memory region. That's the idea. But if you do not call free, after semDestroy, you can once again call seminit if you want to use it, because the semaphore is still there. But of course, you need to call seminit again in order to initialize it and use it again. So destroy does not, as the name implies, actually eliminate, destroy completely, annihilate the semaphore. It simply tells the kernel that you are no longer going to use it. So be careful. First, wait for all the waits to finish, then call semDestroy. And if you are really sure that you are not going to use the semaphore ever again, then free the region of memory that you have allocated for the semaphore. That's the order of things. Comparisons with other synchronization techniques. Now, we are going to talk about System V semaphores, System 5 semaphores later on, not today. And Mr. Nevzat says, can both threads from different processes and another process exploit? No, it doesn't work that way, Mr. Nevzat. Only the threads of the same process can share a semaphore. So if you have, for instance, two processes, each with a certain number of threads, they cannot share an unnamed semaphore. Why? Well, very simply because an unnamed semaphore in this case if it is going to be used between threads, it will be stored as a global variable. And a global variable is not accessible by another process. If, on the other hand, you use a shared memory region, well, in that case, yes. If it is stored in shared memory and you want to use it across processes, well, in that case, yes, you can use it in order to synchronize distinct processes in the context of the same application. But if you're going to synchronize threads from distinct processes using a globally allocated or a semaphore as a global variable, well, in that case, it's not possible because global variables, static variables, are only accessible by the threads of the same process and not by threads of other processes. But don't worry about that. We will talk about threads when the time comes. Right now, it's early to be talking about threads, so you can forget about them for now. System 5 semaphores. Now, at the beginning, I said that System 5 semaphores are more powerful. Why are they more powerful? The POSIX semaphore interface does not support weighting, decrementing atomically for a value greater than 1. The semWeight system call for POSIX semaphores decrements the value of a semaphore by 1 atomically, but just 1. If you want to decrement the value of a semaphore by a value greater than 1, 2, 3, 10, 15, you cannot do it atomically. Just like we saw at the beginning of this lecture, you have to call multiple times semWeight. So if you want to decrease it by 2, the value of the semaphore, you have to call twice semWeight. And calling twice semWeight is not the same thing as calling one atomic semWeight that decreases it by 2. Why? Because after calling the first semWeight, maybe the process will be interrupted and some other process will be scheduled to execute. It is not atomic. So you cannot do that with POSIX semaphores. You cannot atomically decrement the value of a semaphore by more than 1. With System 5 semaphores, you can do that. With System 5 semaphores, System V, System 5 semaphores, you can decrement atomically the value of a semaphore by an arbitrary value n. That is a significant advantage. Moreover, the POSIX semaphore interface is simpler than the System 5 semaphore interface. That is definitely true. The System 5 semaphores are more complicated. That is why we are not taking a look at them today. There are far too many things to pay attention to. Plus, the POSIX named semaphores eliminate the initialization problem of System 5 semaphores. Now, with System 5 semaphores, you manipulate not just one semaphore, but you can manipulate entire sets of semaphores. So you can initialize 10 semaphores at a time, 15 semaphores at a time, wait on 5 semaphores atomically with a single system call. But of course, that requires quite a lot of preparation. So long story short, POSIX semaphores are not as powerful as System 5 semaphores, but they are simpler to use. That's the summary of the entire situation. What about if we compare mutexes with semaphores? Now, we haven't talked about mutexes, and we will not talk about mutexes. We will talk about mutexes when we talk about threads, because mutexes can only be used for synchronizing between threads. They are similar to semaphores, but there are two very important differences between mutexes and semaphores. One is that a mutex is either locked or unlocked. It cannot have another value. Semaphores can have infinite values, 1, 2, 3, 10, 15, 1 million, whatever you want. Mutexes can be in either two states, only two states, locked, unlocked. That's difference number one. Difference number two is that a semaphore is not owned by anyone. Semaphore'un bir sahibi yok. A semaphore is just a variable. Any process that has access to it can wait on it or post it, increase its value or decrease its value. With threads, it doesn't work that way. A mutex can only be unlocked, so increased in value, if you will, can only be unlocked by the thread that locked it. No other thread. That's an important, very important difference. There is a sense of ownership when it comes to threads. So that radically changes the way that you design your programs. But don't worry about it. We will talk about threads and mutexes and condition variables when the time is right. For now, this is just a small educational slide in order to know the differences between the two. Now, there was a question about signal handlers. Now, there is one circumstance in which mutexes can't be used in a multi-thread application, and semaphores may therefore be preferable. Because it is async signal safe, sempost, that function can be used from within a signal handler to synchronize with another thread. Sempost, so posting the value of a semaphore, can be used inside a signal handler. It is safe. It is an atomic operation. It just increases the value of a semaphore, it returns immediately. So you can use sempost inside a signal handler. Mutexes, no. Mutexes are not safe. What about waiting in a signal handler? No, don't do that. Don't do that, because if it blocks, that means your process will block inside a signal handler, whereas we are trying to finish up the signal handler as soon as possible. So don't call semWait inside a signal handler. Sempost, you can call it, no problem. Semwait, no. Okay. And that brings us to the topic of shared memory. Now, I will not talk about shared memory today because it is a distinct topic. We only have 15 slides left, and we will talk about it tomorrow morning. Since we only have 20 minutes left, I don't want to just start the topic and leave it in the middle of it. So I suggest you read about shared memory until tomorrow, and tomorrow morning at 8:30, we will continue with these slides and finish them. And in the meantime, I will start preparing your midterm exam, and I'm guessing that it will be ready in a few days. Yeah. Any questions?
So I have unrelated question from this topic.
Unrelated?
Yes.
How unrelated?
I mean, about signal handlers.
Okay, sure.
As you said, normally, like, we don't do any, like, we want to leave the signal handler as soon as possible. So previously you said just put an integer to in it, so you just raise the integer in the handler, so we know that we are in the handler, and after we can check the integer and we can free the allocated memories.
Yes, that is one strategy. Yes, using a flag variable.
How can we free the allocated memories after? I mean, because, like, where can we check the integer will increased or not in the main process, not in handler?
Well, you will check it. For instance, you can check it every once in a while. You can check it periodically.
But we don't know. Which part of the main is executed at that moment. So
yes, you don't know. So you will sprinkle, böyle tuz atar gibi, karabiber atar gibi. So you will sprinkle those controls all over the program.
So we just write another function, just checks the integer value.
So you can have, for instance, such a function that checks the value of the flag variable, and if it sees that the flag variable is set, well, that means it is time to terminate, for example, and so it deallocates whatever has been allocated up to that point and exits. Or it simply calls exit, and you can have a handler and registered with @exit that will clean up everything. The choice is yours.
You mean exit as a function in the handler?
I mean a handler registered with @exit, the @exit system function, system call.
Okay.
So either you will have your own function for freeing up memory, or you will have a handler registered by using @exit. When and with what kind of a frequency are you supposed to call, or are you supposed to rather make the controls of whether the flag variable has been set, that is up to you. That depends on the program. You can have, for instance, certain blocks of execution that you don't want interrupted. So you can wait until that part is interrupted. But the longer you wait, that means the longer the user waits after pressing, it's the keyboard press. So if you have only 2 or 3 if clauses checking the value of the flag variable in a very long program, that means after the user has clicked press the keys on the keyboard in order to send the signal, the termination signal, that means that user might have to wait, and that will make the user unhappy. But if you have many frequent controls, that means your program will be more responsive. It is up to you.
Okay. Thank you for the response.
Welcome. Any other questions?
Hocam,
Can
ben
we
bir soru
use the
sorabilir
same?
miyim?
Bir saniye. Hüsnü Bey, bir soru geldi yazılı. Sizden önce geldi. Can we use the same handler for both the parent and his child? What do you mean? The signal handler or the exit handler? Okay, the signals come to the child while it is executing. So I'm guessing that you mean a signal handler. Okay, so the signal comes to the child, and if the child has a handler for it, the handler gets executed. Is the handler inherited by the child? If that's your question, yes, of course it is inherited. Remember, the child is a clone of its parent. But when you call exec, that's a different thing. Be careful. We had explained it in the slides. When you call exec, the handlers are cancelled, and those signals are set to their default disposition. Hüsnü Bey, sorunuz?
It was about wait for children.
Okay.
When we wait for children,
Yes.
and if the parent process has more than one child processes,
Okay.
and if you wait for the child processes in a signal handler, which is registered for a sick child signal,
Okay.
when we are in a sick child signal handler and making the wait operation, more than one sick child signal arrives, and they're accumulated, and we missed one or more sick child signal. So it means we are going to miss to wait for child processes. In this case, what do we need to do? Should
Well,
we
first
wait?
of all, you need to definitely block the sick child signal while you're handling it. That's for certain. But of course, this doesn't mean that you cannot have more than one sick child signals arriving in the meantime. So let's say that you have only one additional sick child signal arriving while you're handling it. Now,
Yes.
after handling it, and it is unblocked, it will be delivered. So nothing is lost. But if you have two sick child signals arriving while you are handling a sick child signal, that means one of them will be lost because signals do not accumulate. So two signals will become one signal that will be delivered after it. Now, what you can do in order to solve the situation is that one, inside the signal handler, you can try to wait for any processes, for all the processes that have finished, but which will be very, you can make the assumption inside the signal handler that maybe one, but maybe more than one children have terminated and behave accordingly, which is a bit dangerous. Or you can also play it safe. And at the end of the program, not inside the signal handler, at the end of the program, because the signal handler will return eventually, at the end of the program, you can also have a number of wait calls equal to the number of children. Now, if by any chance you missed a certain child's termination, those waits will catch it. And if you haven't missed any child terminations, well, in that case, those waits will return immediately. So nothing is lost. Anlatabildim mi?
Evet hocam.
Peki.
Teşekkür ederim.
Rica ederim. Any other questions? Mr. Nevzat says, is there a way to overwrite the forked handler for the child? Well, you can redefine a new handler. That way you will cancel the original handler and you will have a new handler. Any other questions? Okay, class. Well, in that case, if you have further questions, you can send them through email. And if everything goes all right, I will see you tomorrow morning at 8:30, and we will continue with shared memory. And I recommend in the meantime that you study from your book on shared memory, SHM, Open, etc. You will see the system calls. They are quite simple, but they are also quite powerful. I mean, we are talking about a technique that allows you to create a shared memory region in random access memory that is accessible by multiple processes. So anyone can write or read from it. So no need for pipes or FIFOs or anything. It is extremely fast. You directly write to memory and directly read from it. So very fast communication, but of course it requires synchronization mechanisms. So we will talk about the details tomorrow. Read from your textbook in the meantime, and I will see you tomorrow morning at 8:30. And I will also start thinking about the midterm questions. What should be the midterm project about? Something that hasn't been asked yet. Something original. Okay, take care everyone, and see you tomorrow.